Okay, as we know in our remote lab, so let me just start from the beginning how it looks. You already know it earlier itself. Let me just start from the beginning. Okay, this is where I'll start. Okay, this is the remote lab front page what we have. So from here we'll start from click to start, and then from here we'll start selecting the experiments. So since we are looking at triple five timer, so let me select this triple five timer. Here we have three different applications of triple five timer. That is a stable multivibrator, monostable, and bistable. So first, let us select a stable multivibrator. So in this stable multivibrator, oh, this window is not visible. Let me just make sure that this is also visible. One second. Okay, how do I make it? I just come down here, share the content. Wait, wait. Mm, okay. Over now. Is the WaveGen also visible? Sorry, AD kit wala. Hope now it is visible. Now, now it's visible. Oh, wait, wait, wait. Just a minute. I can get to know what is visible, what is not visible. Is this now visible? I think it's visible now. Correct? Now let me also just make the waveform also visible. I will add one more content, share content. I hope both are visible now. Yeah, done. Now in this stable multivibrator, let us select three different. Okay, there are 10 possible combinations. Let me select one of them. This is a stable multivibrator. So as it was mentioned in the that copy whatever I just shared, so we can able to vary. Oh, ice is breaking. Just a minute. Okay, let me just, okay, voice, it's fine. So let me just make sure that, okay, this is, okay, okay, then let us start conducting the experiment. So this is a stable one. If you can see here, so as it is mentioned in the what video, we will going to see two different waveforms. One is the output waveform, other is, oh, is it went off? Hello. Why it is going off? Only I think now. I think now it's fine. Okay. What we can do is we can actually stop this and we can start measuring the parameters. So what are the measurement? What are the parameters that we want to measure? Is we want to measure the on time, off time. This is channel one. So channel one, you can able to measure what is the what is the maximum voltage the capacitor can charge and what is the minimum voltage capacitor can recharge. So what are the maximum and minimum voltages capacitor can charge and discharge? Hello, can somebody say something about? How come zero? It is half of VTH, no? VTL. It can't be zero. Yes, this is VTL, that is VTH. So this VTH is the channel 2 voltage, that is Wavegen voltage, whatever you have given. Let me say this positive it, negative it. We'll close this. I just put this over here. I can take out the Wavegen outside and let me vary this simultaneously. See here, I hope it is visible both the waveforms. If I vary this, keep an eye on the top voltage. So how much is, oh, it went off. Let me just make it again visible. It's going off again and again. Okay. Uh, Now what I'll do is I will make this, I'll make this point. Can you see this maximum voltage, C1 maximum 2.29, is it almost close to this? Hello. Of course, you can see what is the minimum. Is the minimum half of that maximum of C1? Meaning VTL is always half of VTH. And that VTH is equal to the control voltage which is applied through channel 2. Correct? Because as per the circuit diagram, so we have the channel 2 is going to pin number 5. So what I'll do is I will change the voltage. Of course, you can have a look at the negativity. Is the negativity is 0.47 millisecond? Now what I'll Now what I'll do, I will increase the amplitude of this. Can you see now it has almost 3.4 volts or 3.36? Can you see what is the maximum of C1? Is it almost same as the external voltage, this one? And is this almost half of that? Can you see this negativity is almost same as the previous case, 0.47? Because why it doesn't change is because negativity is independent of the control voltage. It only depends on R2 and C. Because when I say R2, okay, let me also share that circuit diagram. Where is my circuit diagram? The circuit is here. Can you see it only depends on R2, CT, and of course, can you see this one? There is no question of with external voltage. Only T on is keep on changing. Once T on changes, frequency will change and T will change. Correct? This is what I want you people to do when you are asked to conduct the experiment. Here we are not applying W1. So please note these things. In case of a stable multivibrator, we will not be using channel 1. W1 is not used. That's why you can see it is not running. Whereas channel 2 is used. Using channel 2, you'll apply only the DC voltage for the first operation. That is to understand the stable multimeter. That is, okay, it's disconnected. Like, yeah, I'll just connect it. Can you see now? So we are not applying anything. We apply here. We apply the DC voltage. We will measure what is maximum, what is minimum of channel 1. What does channel 1 indicate? What does channel 1 indicate? Channel 1 indicate not trigger, capacitor charging discharging. It is the timing capacitor charging discharging it is indicating. What does channel 2 indicate? Output voltage. So in channel 2, you are measuring the frequency, you are measuring the positive duty cycle, you are measuring the positive width and negative width. Correct? If I change the voltage, positive width will change. Okay, positive duty cycle will change, frequency will change, and of course this maximum minimum will change. Correct? I will just do the same thing. Let me make it maybe somewhere around. Okay, this is around 1.7 volt. Can you see it's almost same? Almost same, of course. C1 is almost same as that. Can you see half of that? Can you see the frequency has increased? Can you see this is still the negativity is 0.47 millisecond? Can you see the what is that duty cycle has become less than 25%, sorry, 50%? Because we are varying the duty cycle by, of course, we are varying the okay on time by changing the value of the offset voltage. Offset voltage matlab the voltage that is applied to pin number 5, which is the control voltage. Correct? Okay, this is for which combination when we selected, when we actually selected, okay, let me just show you that also. So when I selected the first combination, see here, for this first combination. Now what I will do, I will for the set values, I will change to second option. Can you see in the second option R1, R2 is equal to both are 10K? So let me just go here to second one and start conducting. Can you see the timings have changed? Okay, let me just redo that again. This was my first one. What was the duty cycle? Can you see it is 35%? And you can see frequency is almost 1.35 kilohertz. I will change this to 2. I will start capturing the things and I will conduct. Can you see the everything has changed? Can you see this has almost become 50%? Can you see this is also changed? This is also changed, and you can see the frequency is 1 kilohertz. Now for this second set of R1 R2, if you change the control voltage, if you change the control voltage, on time remains the same. Sorry, off time remains the same. Can you see it is off time here? Even if you change this value, off time will remain same as point. Can you see that it is almost same here? Let me just change this to. Can you see this is still almost the same? Almost same. So this is how you can evaluate the experiment. Even though there are 10 different combinations or 8 different combinations, what you can do is you can stick to 4 few combinations over here and then look for the changes. Look for the changes. Uh, ex, Especially for the board what I have in my home, my diode is not somehow turning on, so I need to fix it out. But you can certainly see these 4 options. So A1 to A4 you can able to conduct, and A5 to A8 will be same as A1 to A4 because the diode is not coming to picture. Let us try to see how does this, okay, VCO is nothing but, so in the same experiment of A1, A2 or whatever the combination, so what you have to do is, can you see this is the frequency for this voltage for 3 volt, is it 550 hertz? Shall I, if I reduce the voltage, does the frequency increase? Hello. If I reduce the amplitude, can you see the frequency has increased from 500 to 800? if I further reduce it, does the frequency further increase? Can you see the frequency has become 1 kilohertz? I will further reduce it to maybe around, okay, zero point 0.6. Can you see the frequency is, okay, let me just make sure that it is, can you see it's almost 1.1 kilohertz? So as I reduce the amplitude, the frequencies keep on increasing. Correct? Hello. Am I there? Hello. 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 Okay, let me just. Okay, now I think it's connected. It's got disconnected, no? Something. Hello. Is it fine now? Is it fine now? Okay, okay. Okay, what we have to just check out for VC voice. Change the control voltage and have a look at the. Is it echoing? So what now? I think now it's fine. Okay, what you have to do is you change the control voltage, have a look at the frequency, that is your VCO. So we will see. Can you see what is the frequency of the signal now? Okay, let us make sure that the uh, just a minute. I will make it 50% close to. I'll make it close to 50%. Almost there. I'm almost there at 50%. Now, with this DC offset voltage, I will apply, what is the frequency now? The frequency is now around 1 kilohertz. I will apply a sine wave of frequency around maybe 100 hertz. The amplitude, oh sorry, this will become 100 kilohertz. Let me make it 100 hertz now. This is 100 hertz. Now I will make an amplitude of almost 2 volt and 2 volt, maybe slightly more. I'll make it 1.8. This is fine. Okay, let me make the frequency slightly lesser. I will adjust the timing so that I can able to see the waveform properly. I will stop it now. Can you see there is a variation in the pulse width? The positivity is keep on changing. See here? Hello. Am I audible? Okay, yes. Can you see now there is a width variation happening? So you can clearly observe the adjustment that you have made here. So what was the actual frequency of the input signal? Sorry, the square wave when we before we apply the sine wave here. So if I apply DC signal, if I apply DC signal, 600 or no, it was 1 kilohertz. Can you see it's almost 1 kilohertz? Hello. The frequency of the square wave is close to 1 kilohertz. Now I need to apply a sine wave. I need to apply a sine wave. I need to apply sine wave so that in that one sine wave, I have to have more than 10 cycles. Getting the point? In that sine wave, I have to have at least 10 such square waves. So if you want to accommodate 10 such square wave within a sine wave, does the sine wave frequency should be 1/10 of this? Hello. 110 means okay, it should be 100 hertz. Now, suppose if I make it 50 hertz, so will I going to have 20 such cycles of square wave within one cycle? Correct? You try to have as many number of square waves as within one cycle. So I will apply a sine wave of 50 hertz. Does it accommodating? Now I will stop here. See from this stop to this stop. So is it one cycle like thing? So this is almost one cycle. So in that, do you have sufficient number of waveforms so that you can able to see the width variation of the pulses? Can you able to make out there is a change in the positive width of the square wave? Hello. T1 is keep on changing, meaning, so this is what do we say it as pulse width modulation, PWM waveform generation. This is possible by applying an appropriate sine wave of lesser frequency at the control voltage using second channel. So this is our second channel. We are applying a sine wave of low frequency with appropriate offset and amplitude voltage. You can able to get what is the maximum. You can able to get a PWM waveform. Correct? Okay. So is that okay? Even though it is said that okay PWM, so we have options something like here. See here, even in A2, I can able to get a PWM. Even in A1, I can able to get a PWM. Even in A1, A2, or any combination, I can able to get a VCO. Simply for sake of giving all those okay, combinations, so we have given it as VCO and PWM. But you can able to see the application of this triple pair timer as VCO or PWM in any of the 8 different combinations. These 8 different combinations are corresponding to different values of R1, R2, and the condition of diode. For 4 different combination, diode is off. For the another 4, it is on. But unfortunately now in my board, the diode is not switching on. You can able to see any of the 4 combination. Correct? Suppose if I select the fourth one, A4, Let me just do that. I will go back to I'll go back to this. I'll put a DC voltage. Let me run this. Can you see now you have the original waveform, whatever we thought of getting. Okay, let me apply something like, okay, 2.4 volts. Okay, let me just see very few cycles. I will see few cycles. Is it fine now? Now, what I'll do, I will I will change the combination. I will change the combination to a different thing. I will select A4. So can you see what is there in A4? Is the off time very less, on time too much? Okay, I'll make it visible. I will make that visible. How do I make it visible? It's here now. Okay. For A4 is R1 is equal to 10K and R2 is equal to almost 900 ohms. 1K in parallel 10K will become 900 ohm, no? Can you see, as per this, the off time is very less and on time is more. The duty cycle should be almost like, okay, 80 to 90%. We have selected A4. Let me conduct. See this. Can you able to see there is a 89% duty cycle? Hello. Can you see this off time is very less? Off time is very less. So I can slightly change these timings and then I can able to make. Can you see the off time is so less? This is happening because R2 is less and R1 is large value. Correct? Okay. This is how we can able to see the operation of a stable multiplier, any combination. So when I ask people to conduct, you have to make these readings and then make the appropriate changes here. So any questions on this? Any questions on this? Anybody? Hello. Is there any question? Hello. No questions? Okay. Then we just move on to the next experiment, that is a monostable multivibrator. So I will select monostable multimeter. Here I got three different combinations depending on the value of R and CT. So CT is fixed at zero point 0.1 microfarad, whereas the value of R is changing from 1K, 10K, and 1K and parallel 10K. So these are the three different values of R. For one value of R, it is 1K. Second option is 10K. The third option is parallel combination of 1K and 10K. It's almost close to 900 ohm. Correct? The CT value is zero point 0.1 microfarad, and of course, we have a differentiator circuit to generate the spikes. Here, what we're going to see is we're going to see channel 1's trigger signal and channel 2 the output waveform. Correct? So let me select this. Okay, here since we have to, there are two possible signals that you can able to give it. Can you see this? Okay, let me just make this. There are two voltages you can apply or you need to apply. One is control voltage using channel 2. Other one is a trigger signal which is a square wave using channel 1. Correct? Using channel 1 you need to apply a square wave. Using channel 2 you need to apply a DC voltage. These are the requirements for this particular experiment. What I'll do, I will go to this using channel 1, I have to apply a square wave. Let me apply, okay, 1 kilohertz is fine. Let me apply an amplitude of 2 volt. That is fine. That will going to give you 2 volt and minus 2 volts. And let me apply, okay, let the DC voltage be this much. Let me run both of them and let me run this also, because now it is still running the previous one. There is no change here. So I had to go to this and then run this. If I run, Can you see now you have the input voltage coming, but output voltage is rarely coming. So that is purely because my trigger signal is not going below VTL. Correct? What are the conditions for mono shot to give the proper output? The trigger signal should go below VTL. So this 2 volt is not making it to go below. I will make it 3 volt. You can see what the change. Can you see for 3 volt it is coming properly? Now what I'll do, I will just make this okay for proper visibility. I'll make this 2 volt, smaller one. I will just push it up. So I will make it to go up by 5 volt, and I'll make this to go down by -2, or I'll make it to go by -5. Will it make sense now? May not be -5. Okay, let me make it -3 volt. Okay, -3. Will it make sense now? So what I do now? See now, is this your trigger signal LO1? And when LO1 goes down, so this becomes that this will become the trigger signal. Can you see this is now in the quasi-stable state? This is there in quasi-stable state, depending on the value of control voltage, the value of RT, and value of CT. Correct? And once the quasi-stable state ends, it goes to stable state. So when it will again go to quasi-stable state, when it is going to quasi-stable state, only when the voltage goes below VTL. Only when the voltage goes below VTL. Of course, this is the trigger signal. Actually, what we'll be getting is there will be spikes coming. So we are not showing that waveform in the remote lab. Unfortunately, I can't switch the points from the trigger voltage to trigger signal to the pin number 2 voltage. So here I'm going to have a spike. So here I'm going to have a spike. Wherever spike is there, you're getting the pulse width, and you have one more spike coming down, so you have a pulse width. Now, does the pulse width vary with the control voltage? Okay, what I'll do, can you see the positive width is how much? Is it 0.14 millisecond? Okay, let me just remove all of them. Remove all. So what is interested is what is this width? So I will add only one parameter, channel 2, horizontal. I will add only the positive because only that positive width is of interest. Can you see positive width is 0.14 millisecond? If I increase this, does the positive width increase? Can you see has it whether it has increased? Can you see it has become 0.23 from 0.14? If I reduce, just have a look at that output voltage. Can you see is it also reducing? Now suppose now it is 0.1. If I further reduce, can you see it is now 0.07? Correct? Of course, let me just show you that okay why it is happening so. Can you see, of course, maybe you can just go to, okay, let me just show you that also. I'll just open that document that I shared to you people and show that, okay, how does that, okay, let me just share this content. Which content I have to share now? Where is my, 1 second, Microsoft Edge here. Can you see here, if I just go down to monostable multimeter, can you see here, this V external? Does the pulse width depends on V external? That's why as I was varying the value of V external, the pulse width was changing. Even though for the same value of RTCT, if I change V external, the pulse width was changing. Correct? That's what is this demonstration. I'll show this also. See now? Can you see that? Is it visible? Perfect. Then what is the other possibility? Other possibility to vary the width. Other possibility to vary the width is if I change RTCT, that will also change. Correct? So what I'll do, I'll go back to my remote lab and I will select a different combination. Can you see I'm selecting second option where the value of RT is 10 kilo ohm. See now if I select it and run, can you see the width is so large? Can you see the width is too much now? This is a positive width. Nico? Now again, if I vary the voltage, control voltage, does this width change? Now it is a width now. So it is actually this is the width. You can see it's almost 0.83 millisecond. Can you see if I reduce this, is it reducing? Can you see the width is reducing? Can you make out? Okay, this spike, whatever you're getting, let me just show you that also. Whatever spike that you're getting here, this spike, okay, let me just show you that again. This spike, whatever you're getting, is because of the input transition. So input is since it is going from 0 to VCC, so that is from okay minus 3 to plus C. So there is a spike over here. So nothing to worry about this. The pulse width is actually this one. The pulse width is actually this. Can we now see the pulse width can be modified by changing either the control voltage or the RTCT? Correct? Can we demonstrate non-retriggerability? Meaning, if I apply the trigger signal, okay, let me just okay, make sure that okay, this is my width. Can you see this is the width now? I will increase the frequency of this to 2 kilohertz. See the change. You can clearly observe what you mean by non-retriggerability. Let me just demonstrate that. I will stop this. Okay, let me just make sure that I have few more cycles. Okay, this is, I'll make it maybe zero point 0.5 so that I can able to have more cycles. Now, can you see here? This is your valid trigger signal, correct? Hello. And can you see this is the width now? This is the width. Okay, I can actually measure the width also. What I'll do is let me take a cursor. Let me take X cursor, place one normal, place one delta. Can you see here? This is my width. This is my width. Almost how much is the width? Width is 1.08 millisecond. This no, this one. Delta X is 1. See now. So this is your valid trigger signal. Can you see there is one more trigger signal coming here? High to low. Can you see there is one more trigger signal coming here? These trigger signals are not considered because whenever you are applying the trigger signal, the output is still in quasi-stable state. What do you mean by quasi-stable state? Output output high corresponds to quasi-stable state in triple five timer. Since the output is high here, when the output is high, if you apply a trigger signal, it will not consider. You can see you applied one trigger signal. Whenever I apply this trigger signal, what is the state of your output? Whenever I give this, just see this. Whenever this is coming, was the output in stable state? Since the output was in stable state, it considers this as a valid trigger signal. It is there up to predefined time of 1 millisecond. Within 1 millisecond, if you get second trigger signal, third trigger signals, it will not consider that. It will not consider because the output is still in quasi-stable state. See here, is this trigger signal considered as valid one? No, it is not considered as valid because it is still in quasi-stable state. Has this ended the quasi-stable state here? Is the quasi stable state ends here? Now it is a stable state. The immediate next trigger signal will be a valid one. Can you see this is the immediate next? Now here it is becoming valid. Suppose if I increase the frequency of my this to maybe around 4 kilohertz, you can see how it happens. I will run this. Can you see I'm giving repeated signals? See here, this is valid, invalid, 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 invalid. Okay, these many are invalid. Why these trigger signals are invalid? Because the output still in quasi-stable state, these will not be considered as valid. Can you see this has ended the quasi-stable state? Now here you are getting the next trigger signal during the stable state condition. It goes to quasi-stable state, remains so and so. Can you see whatever the frequency of your input signal is, the width remains the same constant? Okay, does the width remain constant now? Is it almost 1 point something millisecond? Almost 1 millisecond. See here? This was the width when it was 2K now. Now I made it 4K. The width remains the same because width depends on what? Width depends on only this parameter RT, CT, VCC, and VXL. Since I'm not changing anything, this frequency will not affect. The frequency of the trigger signal should not affect my width. Correct? Done? Okay. That's about monostable multi-operator. So any questions here? Of course, one way of getting a proper trigger signal is ensure that you apply 3 volt, forget about the offset. Otherwise, you can apply 3 volt and maybe apply a 4 volt or maybe a 2 volt offset. So this is also fine. This is also fine if you just okay, start running. You can see if I run this also, it's coming. Can you see it's current? So let me just okay show you that okay where it won't come. So I'll make this also 3. I'll make this also. Let me just make sure that this offset voltage is 3 volt. Are you getting the waveform now? You are still getting the waveform. So what I'll do is I'll slightly reduce this. Can you see it went off? Why the output is not coming? Output is not coming because the spike that was going down, because this trigger signal what is there is not going below half of this. Half of it's not going below 1.7 volt. If you want to get either you can reduce the offset voltage to 2 volt. You can see you're getting, or you can increase the reference voltage. Correct? Okay. Shall we move on to next now? Next one is bistable. Let me select bistable. Of course, in that video, the waveform was, sorry, the circuit was not there. So I could able to edit the circuit. Can you see what are the things that I'm supposed to apply? I'll be applying a sine wave through channel 1. Channel 2, it is the reference DC voltage and output will be a square wave. Shall we do this? I'll go back to my wavegen and I'll apply sine wave now. Sine wave should be of bit lower frequency and let me have this to be 2 on 2 so that it is okay. Let the waveform be sine. Done. Okay, let the offset be this much. Okay, let me go back here and then let me change the frequency so that I can able to see the waveforms. It is not making transition because this okay I have not yet conducted, so I need to conduct the experiment. That's not it's not conducted. No? If I conduct, it will come. Done. Can you see the output is making a transition? So now I can make this as This has zero offset. This also has zero because I need to overlap both of them so that then only I can able to clearly see the things. Is it fine now? I will take out. Okay, let me just remove all of them. I will stop this. Shall I move this one of the cursor? Is this my VT? This is VTL. This is VTH. VTH. Okay, let me take out. How do I take out this? Okay, let it be here. Let me just take this and put it here. Can you see VTH is almost equal to control voltage, which was 2 point. Okay, let me just place this here. Where is my? Is it almost 2.5 volts? Can you see this is also 2.5? Can you see this is also 2.5? See this 2.5. This is 1.3. Half of that, close to that. Correct. Then we can also see the hysteresis. How do I see the hysteresis? Go to add X5. Okay, I will take out this. Can you see this is the hysteresis? See here, this is the hysteresis. If I change the voltage, okay, I'll just keep it in run mode. So if I change this voltage, just have a look at this hysteresis. Okay, VTH and VTL. Is it keep changing? Can you see? Is it moving? Can you people observe this? Observe this. See now, if I'm reducing that, is it also reducing? So if it is 0.57, so that this is okay. Corresponding to that, I'm going to get the waveforms. You can see it's almost. This is 1.72. This is half of that. This is 1.8. This is zero point 0.9. And of course, if it is 3 volt, if it is 3, this is 1.5. Correct? This way VTH and VTL. So this is what we have done in the class also. So we have seen that okay, this is output is always a square wave. This is like an inverting Schmitt trigger. Inverting Schmitt trigger. Correct? If the input voltage exceeds VTH, output is going to minus V set. Minus V set in this case is zero. Correct? Hello. Then we can move on to the Schmitt trigger. Okay, Schmitt trigger. Where can I find Schmitt trigger? Okay, bistable done. Okay, here this is done. I can go to op amps. Where is op amp here? Select other applications. I have Schmitt trigger here. I have different combinations like okay, let me just put this down here so that you can able to see it. This is select inverting Schmitt trigger. Here there are different combinations possible. Let me select invert to 1. As I just mentioned in this doc file, let me show you what is invert 1, 2, 3, 4 stands for. This is fine. Can you see what is this? Okay, invert 1, 2, 3. So this corresponds to values of R1, R2, so on. Can you see this is R1, 1K, 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 10K, 10K, 1K. This is 10K, 10K. So these are the different values of feedback resistors. Because R1, R2 is nothing but this R1, R2. What is R1, R2's? R1, R2 is this feedback resistor and this resistor R1. For different resistor values and control the reference voltages, you can able to get the the transition VTH and VTLs. What I'll do is I'll go back to this. Here also it's a square wave that you are supposed to apply. This should not have any offset. This should be offset of 0. You can apply even an amplitude of 4 volt is fine. I can apply starting with offset voltage of 0. You can start with 0 volt. What I do, I will take this, sorry, this is there. Okay, let me apply. Let me conduct the experiment. I'm not conducted yet. I will select this and then okay. When I start conducting the experiment, this is fine. Let me show you what is the output waveform. Can you see here? This is the output waveform. I can take out this x-axis on cursors. Oh, let me just take all the cursors out. Can you see it is making a transition from plus Vsat to minus Vsat if the input voltage exceeds this value? Hello? Can you see this? Looking at this transfer characteristics, is it inverting symmetrical or non-inverting symmetrical? Can you see this is VTH, this is VTL. How can I change? What are the different ways of changing VTH, VTL as per the equation? As per this equation, or the resistor values. Can you see by changing either R1, R2 value or V reference, I can change VTH, VTL. Correct? I'll go back to my schematic. I'll just go back to this circuit and I will vary this voltage. Just have a look at this. Let me just keep this in run mode. Let me keep this in run mode. I will vary the voltage. See now, if I increase the voltage, does the VTH, VTL will go towards positive? Can you see, are they keep on increasing? Can you see, are they going up? Are they both moving towards right side? If I make, of course, I can make the reference voltage negative also. Can you see it's becoming negative? Correct? Now here I am not changing the values of R1, R2. Keeping same R1, R2 will make this width the same. Can you see this is hysteresis width? This hysteresis width will remain same. Only thing is that VTH will move, VTL will also move by the same amount. Can you people able to understand what's happening if you are increasing the reference voltage? Can you see the width from this VTL to VTH? Does it remain constant? This hysteresis remains constant. Only thing is that VTH, VTL will change. Now, if I change this reference voltage, sorry, if I change this, where is that? If I change the R1, R2s, instead of T1, if I select T2, which corresponds to different values of R1, R2, and if I say conduct, just have a look at this. Just have a look at this width. Can you see it is this much width? I'll go back to this and then change this to. Can you see the width has changed? Hysteresis width. Why the hysteresis width has changed now? Because we have changed the values of R1, R2. As the value of R1, R2 changes, the hysteresis width will change. Now, suppose if I change the amplitudes, I can able to make VTH. Can you see both VTH, VTL are positive now? This is VTH, this is VTL. Are they both positive? I can make it both negative also. Can you see I can make it both negative? Hello. This is zero, no? This is zero. These two are negative voltages. These two are negative voltage. So here the important thing is we are for a given selected value of R1, R2, we are changing the reference voltage, noting what is VTH, VTL that you can compare with your theoretical value. If you change R1, R2 to a different combination, now let me just select to a third combination and then start conducting. Can you see the width has increased too much? Can you see now the width is hysteresis width is too much? So can you differentiate between the first, second, and the third? So there you are changing the reference, sorry, the R1, R2. So that's why naturally the hysteresis width is changing. Hysteresis width is changing. So you have to do different combinations and then maybe two to three different combinations and find out what is VTH, VTL, theoretical and practical values. So I will, of course, you have to be careful while finding the theoretical values also. VTH, you consider this value. So what is VTH now? Suppose if I ask you to add some normal, one more normal. What is VTH now? VTH is actually equal to, uh, uh, let me just show, not VTH, let me just plus VSAT minus VSAT. Plus VSAT is 2.9 volt, whereas minus VSAT is, sorry, wait, let me just stop this. What is VTH, VTL? Can you see VT, so not VTH, VTL, is minus VSAT is minus 3.6. See here, this is minus. Does this corresponds to minus VSAT? Does this correspond to plus VSAT? Hello. I can move this cursor and try to find out what is this voltage and what is this voltage. What is cursor 1 voltage now? Cursor 1 voltage, does the output is making a transition from plus to minus? From plus, is it not going to minus at input of 2.4 volt? At this voltage, is the output making a transition from plus to minus? That is VTH. So at a voltage which is equal to second cursor, where is second cursor? This is 2 point, sorry, minus 3.6 volt, correct? What is, sorry, it's not, what is this voltage now here? What is this voltage? C1 is minus 3.6, minus 3 point, minus 3.5. Output is having a transition from minus VSAT to plus VSAT. So what is VTH, VTL now? The VTH, VTLs are VTH is 2.4, whereas VTL is minus 3.5, minus 3.5. Correct? Okay. So that you can measure here also. This is your VTH value. This is VTL value. So how do I measure from VTH, VTL from this one? If I just expand this and then make sure that this is going somewhere here. Is this my VTH? This is 1, 2. This is almost 2.5 here. So is it to minus 3.5? Minus 3.5? Is it almost there here? 2.4 and minus 3.5. These are the voltages that what you can able to measure here as well as here. Correct? Am I there? Hello. Okay. Similarly, you can try out for hello. Similarly, you can try out for okay when you conduct. Hello. Of course, when you are conducting the experiment, make all this measurement properly, and then of course, whatever that I just showed for the inverting Smith trigger, same thing is valid for non-inverting Smith trigger also. Non-inverting Smith trigger also. Fine. So maybe from tomorrow, I'll just give the access to students. Okay, you people, group wise, maybe group one, group two, group three. So I just want to keep people to just conduct the experiment again through any desk. So of course, it's not that okay, I didn't do or okay, I want all of you to just uh, fill in this table. Where is that? So we have this table, no? So all of you can able to complete this. Oh, sorry. Mm, all these theoretical values you can able to. Okay, let me just share this also. Mm, where is that? This one. Hello, hello. Am I audible? Hello, 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 hello. Am I audible? Okay, all of you calculate the theoretical values and then try to fill in this table and then hello. Am I audible? Hello, hello.